Hello, we are looking at a fluid dynamics concept of Bernoulli's equation. And Bernoulli's equation could handle a situation such as this. Let's say this is a section of a pipe. This pipe changes height. The fluid is flowing from down here up to this higher location, so the pipe increases height. And the cross-sectional area is wide here, but it necks down to a smaller area. And Bernoulli's equation allows us to understand what's happening with the pressure and speed and basically the energy of the fluid flowing through this pipe from one section to another. And this would allow us to know how much pressure we need to do to make this happen and all kinds of different things. So here's some key ideas we need to be okay with before we start. You can have equivalent volumes with different cross-sectional areas and different lengths of those cross-sectional areas. So area 1, which is shown in yellow here, is wide, has a wide area but a small length. That could be the same volume as this blue volume up here, which is long, but it has a small cross-sectional area. So we could get equivalent volumes of those two different things there. Also, density is mass per volume, and we can get mass by density times volume. I will designate volume with a capital V and speed with a lowercase v. Pressure is force per area, so we can get force by pressure times area, times cross-sectional area. So pressure applied across this cross-sectional area is going to be a force pushing on this side. Okay, and also work is force times distance, or the dot product of force times distance. And we know if force and the displacement are in the same direction, that would give a positive work. And if force is against the displacement, that give a negative work, or you're taking energy away from the system. And work, if work is force times distance essentially, and force is pressure times area, we could add these two things or combine these two things and get work is pressure times area times distance. And lastly, if volume is A times X stuff, we could say work is pressure times volume. Okay, so anyways, here we go. Let's analyze this situation. We're trying to relate the energy of the fluid coming in this side to the energy of the fluid coming out that side. So if energy is conserved, then we should abide by the conservation of energy equation, saying if you have more energy here, it had to be because you did some kind of work for your system. Okay, so I'm defining height 2, volume 2, length of volume 2, cross-sectional area of volume 2, and speed of volume 2. And then we have height of volume 1, speed of volume 1, cross-sectional area of volume 1, and length of volume 1 here. So we're going to compare the energy at position 1 to position 2. All right, so to start us off, we're going to do energy conservation. And so I'm going to say the work at position 1 plus the work by the pressure pushing on the fluid at position 2 is equal to the change in potential energy of a volume of fluid. Okay, now let me slow down just a little bit. So if this, excuse the bell here. So let's talk about this. So if this pipe is full of fluid, and we have one, and it's, let's just say it's water, because water's incompressible and it behaves like we're familiar with. Okay, if this pipe is full of fluid and we got a little volume of fluid being pushed in to this green section, Okay, if we have a volume of fluid being pushed into this green section, then that must also push out an equivalent volume over here, okay? And we want to compare when a volume of fluid comes in the left-hand side, what's the energy like when it leaves the right-hand side? Okay, so these are going to be equivalent volumes we're going to talk about as this volume of liquid or water goes in here and comes out here. What's the energy difference, basically? So we're going to use conservation of energy. Okay, so we have the work put into pushing it through this section must be equal to the change in potential energy plus the change in kinetic energy. All right, so next thing we're going to say is, well, we've got a force at position 1, and that's going to be pushing across a distance 1 to push that in to this green part. So there's going to be some work done in pushing it into the green part. And on the other end, there's going to be a pressure pushing this way against that fluid when it comes in, and it's going to be pushing against as that volume of fluid gets pushed out the top here. And so this pressure is going to be pushing this way, and we're going to displace this way, so that's going to be negative work. So that's going to be the force at position 2 times the displacement at position 2 of that volume of fluid as it makes its way from here up to here. So we have some work being done. We have positive work here versus negative work here. Okay, and our UG stuff, well, we can write that as M2, so our change in potential energy, it gains potential energy here, GH2 minus M1GH1. So it's going to gain potential energy. And we can go over here and talk about the change in kinetic energy. That's going to be 1/2 M2 V2 squared, that's speed, minus 1/2 M1 V1 squared. Okay, so from our continuity equation, we know that this is actually going to be going faster because the cross-sectional area necks down. So it's going to be going faster up here. It's going to gain height. It seems like we had a gain in our energies when it goes from position 1 to 2. That's probably because we did more positive work here than the negative work here, or there's a difference in pressures, and we'll see that. Okay, so from here, we can do some fancy substitutions. We know that force is pressure times area. So we can say pressure 1 times A1 times X1. Okay, so we're just substituting out this F for P and A stuff. Minus pressure 2A2 X2 equals, and then we're going to make a little fancy substitution here. Mass is equal to rho times V, and we're going to do that for over here too. Mass is equal to rho times V stuff. And so we can rewrite this, and that's going to be rho V2, that's a volume. These are volumes. I'm going to make them capital V's with this little fancy look there. Okay. Times G times H2 minus rho times V1 times G times H1. And then we're going to say plus 1/2, and we're going to write rho times V2 speed 2 minus 1/2 rho times V1 speed 1 squared. Okay, and the density of the fluid is the same fluid the whole way, so that's going to be, I'm not putting density 1 or 2, it's just the density of the fluid the whole time. All right, so we've switched some of our stuff around here by making some substitutions. I'm going to do one more substitution, and I'm going to say, hey, our volume is really just cross-sectional area times x stuff. So I'm going to rewrite this another time. This is going to be, so this part is what I'm substituting out here. P1 V1 minus P2 V2 is equal to rho V2 GH2. Thanks for your patience here. Rho V1 GH1 plus 1 half rho V2 speed 2 squared minus 1 half rho. Whew, this is a big equation, isn't it? Okay. All right, so we've replaced some stuff with these V's here. Now, we know that the volume in must be equal to the volume out. So these are just all the same volume. So I'm going to go ahead and cancel out some stuff. So every term has a volume in it, and those are all the same. So I can go ahead and just cancel those out everywhere. What do we have left? We're almost done. You're doing so good. Thanks for hanging in here with me. Rho GH2 minus rho GH1 plus 1 half rho V2 squared minus 1 half rho V1 squared. Okay, we are so close. And now we can rearrange this to compare the energies at position 1 to the energies at position 2. And so we can put all of our 1 stuff on the left and all of our 2 stuff on the right by doing some algebra. Thanks for your patience. And here's your Bernoulli equation. And basically it allows you to compare your pressures, your potential energies, and your kinetic energies at one part of a fluid flow to another part of a fluid flow. So if you have a oil pipeline, you need to know how much you need pressure, you need to move that stuff around, or you have a water pumping system or whatever, you can use Bernoulli's equation to talk about the energy conservation as it moves from one part of that pipeline to another part of that piping system. All right, so there's some insight on Bernoulli's equation. Thanks, everybody.